Sounds like the cat's ready for a stream. Tuco, you really just want to play with the bolt all the time. That's kind of how this cat rolls. Whoop. Sorry for the video dropouts. There's a loose wire on here. Alright, this is a little later than I usually stream. I was having some problems related to Windows updates not completing. Hey Tuco, and you sure are talking a lot. Anyway. So anyway, I had to work around this this situation. It's been stuck at 9% for a little while. This is usually the machine that's in charge of recording from the microscope. So, that is, I'm probably going to leave that overnight and see if it finishes, and if not, reset it and hope it comes back. But, in the meantime, I had to find an alternate solution. But I've got the microscope recording again, and I am now ready to get back to work on this Ethernet and voltage glitching project over here. So, for a little context, this continues from this is kind of one of the longer projects going on currently. So this kind of picks up after the voltage glitching over USB in the previous edited video. And there I was trying to get firmware out of a microcontroller that mostly communicates over USB by injecting a fault, a voltage glitch, to disrupt its operation during a particular part of the USB descriptor handler, so that when it normally just hands back a chunk of memory that happens to describe the USB device, if I glitch it at just the right point, sometimes it hands back a chunk of memory that has an arbitrary large blob of firmware. If it disrupts the length of that chunk of memory or the pointer, then it'll just return some other thing that's in the same space, which is, in this case, firmware that we might be interested in. So this is similar, but instead of with USB, we're using Ethernet. So there's a bunch of other complications that and the other aspects of this microcontroller end up introducing. But right now we're in the process of transferring a test setup which was working at least to get 64 kilobytes of firmware out of the device under test. I had that working for a kind of fake device under test running example firmware, and now I'm kind of getting the test setup working, well enough to use on this programmable logic controller that uses the same microcontroller. So I should really have this camera going too. This is what the PLC, the programmable logic controller, usually looks like. I just glued the extra parts in here just to have kind of a mock-up. And it's got a set of inputs and outputs. It has Ethernet. It runs a little web server, and it also communicates over their own S7 protocol. There's a little local interface consisting of some arrow buttons and a little graphical LCD with a color backlight. Has a little expansion bus for basically I/O expanders and extra screens and keyboards. So there's a number of changes I've been... Hey, Tuco. There's a number of changes I've been putting this board through in order to get it set up for these glitching experiments. And I've been through a handful of those on the stream already, but certainly not all of them. The biggest change that you'll notice is all of this soldering around the CPU, and that was to separate the CPU's 3.3 volt rail from the rest of the board. And that may or may not actually be necessary. I did it for investigative purposes at the time. But right now I'm mostly interested in the CPU's 1.8 volt. Right now I'm mostly interested in the CPU's 1.8 volt core rail. So that right now is coming out on these SMAs via this little wire, but we'll want to replace that with a nice solid connection to this glitch board, which This is how we'll actually introduce the voltage glitches through these MOSFETs. And it also has some ports that let us stick oscope probes in there pretty easily. So the most recent change here is this morning I adjusted the mounting. I found a spot where I could glue the LCD on. So normally this is a stack of boards that fits in under the case like that, with a keyboard board, and then a control board, and an I/O board. But that was super annoying to work with in this test harness, because any kind of interaction with the UI ends up, vibrating the whole board stack. And having the LCD and the buttons accessible means losing access to all the interesting signals here. So I just got this set up where I found, a spot where I can mount the LCD kind of out of the way. I was thinking about having to build an extension for this flat flex, but there was just barely enough room to kind of sit it where it's not really in the way of anything, and it's hot glued to an electrolytic capacitor there, so it's kind of stable. And that doesn't really need to take a lot of force, it just needs to keep the flat flex from breaking. Oh, he was rummaging in that box for a bolt. So then the other change is so this connector plugs in. So yeah, the user interface was this connector, which is a 30-pin flat flex for the LCD and backlight. And then here is this is a 2 millimeter pitch 2x5 connector, which that would usually plug in right here, but I stole the connector off of it to build this a little adapter. So I just made a little breadboard replica of that circuit board with the same 6 buttons that plugs in here. So now I can work on the UI here without having to vibrate the whole board. My program name is blank. But now this should get to be pretty interesting because, well, to back up even slightly more, I guess there are several factors that led me to want better access to this board. I was thinking about how to mount the glitch adapter, and so I was wanting to make sure I had a good place to put that where all the interesting signals would still be accessible. So I think I'm going to end up attaching the glitch board roughly like there, but this wire is probably actually going to go on the bottom of the board. So then I'll probably just hot glue these two boards together edge to edge as a semi-temporary connection. So the other thing, so the roadblock I hit last time I was streaming about this, so there are several steps along the way to get from a totally unmodified board with this processor to something that I can semi-reliably glitch into returning some of its firmware. And one of those steps, let's see, how do I want to go there? So one of the steps that I took in order to make the firmware, it a little easier to generate glitches with a predictable phase relative to the CPU clock is that I slow down the whole system so that it's not quite as demanding to generate the very fast rise times that I would need, and the timing just generally gets a little easier when you slow everything down. So in my other test setup with the eval kit, I was slowing it down by a little under 25% or so. Let's see, I should calculate what the slowdown was, because I always forget it off the top of my head, because it's a really weird number. Because it's... oh, what's the reciprocal of that? It's like a 22.5% underclock. So the processor that normally runs at 120 megahertz, I was running it at 27 megahertz. But that means that the external clock speed that would normally be 25 megahertz was 6.65, or that means that the clock frequency that would normally be 25 megahertz external to the chip ended up being 5.65 megahertz. So this is currently running, I think right now I have that running on that underclock, so that's why it's actually, the UI looks a little sluggish, because it is actually running much slower than normal. I was having some trouble before with interference on the LCD, but I think that might have just been noise of some sort or a bad connection, because so far this thing seems to be behaving as far as the LCD is concerned. But the problem I was running into before is the web server just doesn't respond when it's running this slow. And it starts responding when I turn up the frequency up to about a 50% underclock or so. And there's a point kind of on the edge where it responds unreliably. So that was a big red flag. So anything where I turn down the clock rate and something behaves differently indicates that I'm dealing with a system that isn't entirely described by that one clock. So either it has some other clock in play, or there are analog components in the system that are dictating where it's stable and where it isn't. In this case, I think it actually has to do with the real-time clock on this device. So I don't want to take this board off just yet. We can zoom in. Alright, so this chip with all the weird soldering on it is the microcontroller. This has a built-in... so this chip normally runs on a 25 megahertz external crystal, which would sit over here. And you can see I've replaced it with a resistor and a jumper wire that goes off to an external clock. This chip also has a facility for an external 32 kilohertz clock, which is usually used for a real-time clock. But I suspect that this processor didn't have the low power features they wanted, or perhaps they just wanted a separate part for ease of use or reliability. So this chip actually, is a combined 32 kilohertz crystal and a little real-time clock and SRAM module. So we'll take a look at the datasheet for that in a sec. This chip, so I think this might actually be... So one of the tests that I'd like to do soon is to inspect the bus on this chip to see how it's being used. I suspect it might be used to time some kind of main loop so that it executes at a well-defined period. And I think that that main loop might actually be servicing HTTP requests in this firmware as well. So one thing I'd like to do now that we've got access to this circuit while the LCD and everything is also accessible, I'd like to break out some more interesting signals on these empty header pins. So we've got these three interesting serial devices here. We'll take a closer look at each of these under the microscope and get data sheets probably, but just off the top of my head, I think this is a flash memory which stores the actual PLC program. This is an MRAM, which is a non-volatile memory that acts like RAM. It has fast read and fast write, but it still retains the data when the power is lost. So I think this holds volatile state for the program, the PLC program. Then this is just a clock. It also has some bytes of memory, I think like 8 bytes. So I think this chip also has like 8 bytes of SRAM in it. So I'm curious whether they're using that for anything, but I suspect that they're just using this as a clock. But it might be that if they are using this as a time base for their loop, and it's causing the web server to break when we slow down this chip but not this chip, then maybe we end up having to remove this and replace it with an emulation that returns the timestamps we want. So if it gets to that point, then there are a number of ways we could do that, either with a microcontroller that's programmed to operate as an I2C slave, or possibly an FPGA, since I've already got one right here doing clock division. So a bunch of options there. It's unlikely that we could just replace this part with some other I2C part that would be protocol compatible, because it's got a hard-coded address, and it's probably easiest to do an FPGA emulation if we end up having to do that. So let's see. maybe I will, well, I wanted to poke around in the UI just a smidgen before powering this off, but I think the next interesting bits are on the back side of this. So the UI is much more pleasant to use with these big clicky tactile switches. I think even with this thing fully assembled, the switches are a little mushy. Yeah, these are super long, which might be for isolation reasons, I don't know. It might just be that was their mechanical design. So we can see the network. And there's the firmware. Anyway, that's what it normally does. And here's a screen we were playing with earlier that lets us send manual inputs into the program. So those you have to hold down this escape key, and then there's the relay. And you can definitely tell that it's stretching the pulses quite a bit, and it's there's quite a bit of lag, and it makes the order of operations a little clearer when it's this underclocked. And the top one is the one that I took the relay, or I cut the trace leading to the relay on that one. Alright, and I have the Ethernet disconnected right now because I don't think it's working, and we'll take a look at that after doing some more instrumentation. Because there's a lot to debug, but right now my focus is on making this whole thing easier to work with. So yeah, I just mounted this thing on this board in this way that makes it a little easier to interact with. And now it's time to, I think, do a little bit more PCB surgery. So, let's see. So we'll want to be getting the signals off of those 3 serial chips. I think I already have some diagrams with that partially traced out that we can refer to. And then the signal here is the 1.8 volt V-core. And I'm going to leave these SMA jacks on here just because they'd be really hard to take off. But I don't want these connected to V-core because this is just, you know, this is just going to be like a transmission line stub, if anything, so it's not going to do me any favors. And I think want to just connect, well, so my goal with the glitch adapter rework is I want to connect the glitch adapter to vCore, and I want to find any capacitors on vCore and remove them. So I don't think there were any obvious capacitors for vCore on the top, but I think they might have a polygon fill on an inner layer that distributes vCore, and so I think there are at least a couple of capacitors on the back we're going to need to find with the multimeter and then remove. So I think that's the next step. Oh, it might be good to look at some of these diagrams on the screen before pulling the hardware off, since I think I have those ready too. Oh geez, except the cat is sitting right on top of the laptop. Well, that's where the diagrams were, so maybe we'll do that in a sec. Okay, cat, you win again. You're in charge. Oh, such tangle in my anti-static strap. Yeah, so one thing I wanted to point out on the back of the board, actually, well, not the back of this board, but the board underneath it. Well, so we can actually take this apart now. Until recently, it was kind of a pain to take apart and put back together, but now the LCD is stuck on there in a way where we don't really have to remove it to get anything interesting. I'll put this on in a sec. This is easy to take off. We can just put that aside for the buttons. All of these will come off in one piece. This is clock. reset and trigger right now, but I might tape additional things on there in the near future. And now this thing comes off and the base is glued down separately. Cool. So then on here, we'll take a closer look at that in a sec. So this is kind of, this was a useful clue. So on this board, you can see it's mostly relays and power supply stuff. I think this is something related to the inputs and outputs. But you'll also see down here, this is a supercapacitor. So that would be used for battery backup of something. So we'll take a look at this again on the diagrams because it's actually easier to see there, but I traced out what this supercapacitor connects to, and let's see if you can actually see it here in real life too. Ooh, it's hard to see without the overlays. I can get it on the multimeter though, because I happen to know which pin. Let's see if there's any voltage on it, just for fun. 3.1 volts. And so I think that goes, yeah, 3.1 volts right there. So that just goes not quite straight through. There's a, I think, a current limiting resistor. Yeah. So there's a 100 ohm resistor, which you can point to it with the probe here. You can barely see it in this shot. So there's the ultracapacitor, and then right there is a 100 ohm resistor, which just acts as probably, I think that's both the resistor that limits charge current, and they also place it so close to the supercapacitor as a safety feature, so that if anything shorts out over here, it's limited by that resistor. And then if you look at where that goes over here, oh man, this is also really hard to see without the photoshopped overlays. I'm cheating again because I already know where the trace is, but and this will be better for the microscope anyway, so we'll probably take a closer look at it there. So that's the trace that would usually go to the supercapacitor. It goes over here, it's this big thick one. There's a via right there, and then another via right there, and some decoupling and a test point. And it turns out this goes to exactly two things. So that via was this, and this is a Schottky diode that it charges through. So on the other side of this is the normal 3.3 volt rail, which happens to be where I grabbed the 3.3 volts for the processor via this resistor. So this diode happens to be what charges the supercapacitor while the external power is available. But then this bottom via is always powered up by that supercap even when the external power is gone. So then if you follow that under here, it goes to this chip. And so I was having trouble locating this chip just with the number markings, but once I started to assume that this was a real-time clock, then I started to Google combinations of the numbers on there and real-time clock, and then it actually came up pretty quickly. And it turned out to be a part by Epson, and they make a bunch of these little real-time clock modules. Oh. I think we're running out of things to see with the DSLR. Alright. Let's make room to get the scope over here. do really think we should look at the diagrams before just tearing into this board, though. I might have to move Tuco. I also need to figure out how to rig all of this so that the microscope is at a usable height. And I think Tuco especially likes that one because it's the power book. It's like the fancy laptop that work got me. Satisfying. There's a moth that found my studio lights. Okay. Hey, Tuco. You're not gonna like me. I know you like me right now. But can I pick you up? Oh. Hey, cat. What do you think? How was your nap? Can I get the laptop now? Oh. Wow. When? Still at 9%. Hello, this channel. Do we have this channel? Oh, I think we want this channel. Turn off some of these overlays. It's the worst touchpad. Okay. Just a moment. Okay. So I made a bunch of scans of this board. So this is the unmodified top of the microcontroller board. Oops. If I get my face out of the way for a sec. So that's what the processor looked like before I gooped over it with a copper. You can see they stamped what looks like a hash and a date code. So that's the real-time clock, flash memory, MRAM. That was the grounding connector that I removed to make room for those SMAs. Ethernet, transformer. That's the expansion connector for additional I/O modules. These capacitors are both for the switching power supply that goes from 8.8 volts down to 3.3. And that's the LCD and backlight. It's a 30-pin flat flux. And then this is the buttons on the front panel. There's this unpopulated connector which, along with some of the unpopulated components for it, it seemed to be an input for that same kind of connector as the sort of expansion on here. So even though this particular module wasn't really designed to take a sort of GPIO in from another thing, I used that to get some hints on how that protocol might work. 25 megahertz crystal here, also removed. So then, yeah, I've also got a scan of the bottom of the board, and composite scan with both sides. This was really useful for tracing things out. So this is where you can actually see pretty clearly the as I say that, I really wish I could zoom in more with this particular tool. Let's actually open that instead of just previewing it. So yeah, this is a surface mount connector for that top board to bottom board link. This is the pin that went to the supercap. Then you can trace the thicker signal down here. And then this is the Schottky diode that pulls it up to 3.3 volts when the power is available. Then for here we have a capacitor to ground, another capacitor to ground. It's a little hard to see what's going on here, so I might take a look at just one layer. But I think that's mostly filtering. Oh, you know, this might be part of a... Unless I'm just seeing something that seems to be related because of looking at both layers at the same time, it might be something related to detecting whether that power is available. I think I'm mostly going to ignore that, though. Bottom layer, why are you on my other monitor? Yeah, I think some of this is just hard to see. Yeah, so the bottom layer makes it a little more clear. You can see that this trace is, so on the bottom layer it's a little easier to see the trace just going from this pin, then down here, just to that via, and then, so we saw that this via just connects to that Schottky diode. It goes straight through here, test point, then this capacitor, and these three vias. So let's take a close look at the other side, but we should just see that powering the clock chip. So yeah, that was this capacitor here. So this makes it look a lot like we have plus 3.3 volts from the supercap on this pin, and that this pin is ground. So let's take a look at the data sheet for that part. So here's again what the top looks like. R810 seems to be the relevant part. goes back. All right, so I really don't want this to be too up. Oh, it does that automatically when you full screen, I see. All right, so this is what I found when I looked for an RX 8010 real-time clock. And then looking at the pinouts, it seemed to be exactly what I found on the board. So this was, it's even easier to see in the composite. So pin 1 is at the bottom left, or bottom right. So imagine this is upside down. And maybe I should turn the photo upside down. It's just so easy to rotate either. I rotate this. I like that it rotates the part that I'm zoomed in on. That wasn't entirely what I expected it to do, but it's what I wanted. I don't want to edit this, but whatever. Anyway, so pin 1, then this thick trace coming in from over here through this test point is the battery-backed 3.3 volts. So it comes over here, that's our VDD. It's also connects to this via on the no connect pin, which seems weird, but maybe there's another reason for that via. It might connect to something I'm not noticing. Then doesn't seem like it uses the IRQ signals as far as I can tell. The only signals I actually see coming out of this going to the processor are these two right here. These two look like they might be related, but they actually go straight through to these LEDs. And these are like Ethernet status LED signals, so they're not relevant here. So it looks from this investigation like this is probably the part we're into, and that it's only being used through the I2C bus and not through the IRQ pins, which might help us in emulating it. So we definitely want to break out this SCL and SDA. Let's see, what else we want to look at on here? vCore for sure. That's the other main modification to make. So vCore, let's grab another data sheet. So I guess I also made the decision to rotate the page instead of the photo here. I didn't want to do that. No. Go away. Alright, so there's the chip, the TI processor we're working with. And the power rail we're looking at is VDD-C for core voltage. There are two VDD-C pins, this one and this one over here. So this VDD-C should be right next to the oscillator pins, and so you can see we can't see what's going on. It just goes somewhere internal. And then over here, just count from the end. 14th from the end. So then, same story here, just go straight in. So we can look to see if there's any vias visible on the back side of the board through this composite if we orient it the same way. Alright, so top left is on the top left. So, same story, VDD core over here below the oscillator pins. So that'll make it this pin. It's probably none of these. I mean, it might be this via, but I think that via looks like it's connected to the ground plane on the bottom side. So it's probably just an internal trace connecting the two, like across all of this on the layer underneath the chip. And then if we go over here, 14th from the left, we get this one. So that could be this pin. So it could be these capacitors on the back. I think what I've done so far, I don't think I removed these capacitors. I think I just soldered a wire directly to this pin on the top side. And I don't necessarily want that to stay, so we can probably just remove that. Hey Tuka, I'm stealing your beer. Well, having that wire in place to find those capacitors is probably helpful. Let's take a quick look at what I've done on the top, but I think our soldering is actually going to be on the bottom. Okay, so getting our bearings. You can't see any of that, sorry. Tuco, I hear you. Okay, there's the crystal modified with its series resistor. Oh, I need more light. Yeah, so if you count over 14th from the left, that's the one with the gross wire soldered directly onto the top. So I'm going to leave that on there just for now for the sake of using as a multimeter continuity test point, but I'll be taking that off in just a sec. So I think the capacitors we're looking for are around here, but because there are some, like, we don't have any visibility into the signals under the CPU, so it's possible they have capacitors near the other VDD core pin also, and so I'm just going to test to see if I can find anything with continuity around here. Hey Tuco, I hear you. Is that V-core? 0 ohms, says the meter. Well, we even have a test point. That's convenient. That's a pretty nice ground. Wow. Well, let's mark these. Oh, Tuco, you're standing on the keyboard and making all the noises. Okay, those are coming off. And that's a great place to attach the glitch board. Where's the other side? So So this neighborhood over here might be the other vCore. I'd also take those off and see if it starts oscillating. I think my tip probes are a little dirty. Oh no. Kyle mentioned in the chat, apparently if I try and watch the stream and listen to music at the same time, something makes the OS X kernel deadlock. Man, I hate those bugs. I find stuff like that occasionally. Meow. You know, they might only have these. They don't necessarily need a ton of capacitance here. I would expect if they had others, they would be around here. Oh! Cool. It does look like they're treating vCore as something polygon-worthy in their PCB designs. They probably gave it some polygon on the internal layer. Well, I don't think I would expect to find vCore anywhere else. I would expect to find at most 2 groups of capacitors, since there are 2 pins. Whoops. Don't want to take that one off necessarily. Okay. Let's try that 2 soldering irons trick for taking things off quickly. Let's warm up my Weller over here with its big tip. We won't need a small tip for this. Oh, Mikey asks in the chat, are there other cats in the building? There are a lot of other cats in the building. Yeah, I think a lot of the time he wants to go outside and hang out with other people or other cats. But right now it's kind of late, so I doubt anybody else has their door open right now. Alright, I think we might have some heat for these irons. Oh man, this tip on the right is huge. And not very warm at this point. Come on, iron. Maybe also needs some solder. Just checking the temperature on that iron. Oh, the one on the right is the ground plane. Okay. You really want something. Okay. That marker did not last long. Okay. So, capacitors done with. Let's find a place to physically attach this glitch board. Tuco's scratching at the door. I wonder what he wants to find out there. Might have to overlap this slightly. Yeah, I think that's where it goes. So I think I want to clamp this a little bit, and then it's tempting to use epoxy because it's such a small area. It might need to be stronger, but I'm gonna try hot glue just so that it's easy to remove. But I do think it'll need a little bit of clamping. Hey, Tuco, do you want to go outside? It's kind of tempting to use a drop of super glue. There's already something kind of sticky on this board. I think it was residue from some tape. Maybe it's all just flux. Oh, there's got to be somewhere to clamp this. Not safely. I can tack it together with a little bit of glue, and then give it somewhere sturdy to be. Actually, I think what I want to do is tack it together with a little bit of hot glue, then wick a drop of super glue in between the two, and then put a little bit more hot glue over it. I think that might give me the right balance of longevity and ease of removal I'm looking for. It's also tempting to do this with solder or some kind of tiny screw. Maybe epoxy is the right thing for this job. Or double-sided foam tape. No, that wouldn't be enough overlap for that to work. Yeah, I think I've got that set so that super glue will seep in that gap. Yeah, so that what I mostly want is for the super glue to wick into the gap between the two. That seems to be what it's doing. All right. This needs a sec to set. Oh man, what else goes on here? I mean, breaking out the pins for those memory chips should be pretty straightforward. And I think putting the glitch board on at this point is going to be pretty easy too. I'll probably want to also glue some standoffs onto the bottom of this just to match the height over here as much as I can so it doesn't wobble around as much. Like Kyle comments in chat, if the board is made with lead-free solder, you don't need passives, just vary the thickness and spacing of your tin whiskers. That's a great strategy. We should get right on that. Okay. Oh, maybe this is, you know, did I ever explain the time travel in the stream title? I feel like I was kind of getting to that and then I got sidetracked. So the real-time clock, I think what I might end up having to do with that is create a fake real-time clock that every time you read it, it returns a time that seems to have advanced by some amount. So effectively creating a little time travel bubble that the device under test and whatever apparatus I want can kind of hover in together. So kind of like a virtual machine where the virtual machine might have its own slightly unreal notion of time, but you want it to be internally consistent between all the different parts of the virtual machine. Hey Tuco, do you want to play Bolt? What do you want? Are you just hungry? Okay, you get to eat something. Well, maybe he's just hungry. You know, I guess there are other things in life than Bolt. So, put some hot glue on this side. Just a little bit in that crack. Something like that. All right. So, I don't know how much further I'm going to get on this, given that it's pretty late and I now have to wait for a bunch of glue to dry, or at least dry enough that I can handle this thing. I think I can at least talk a little bit about the next couple of steps. So, what I expect to see, so I want to get a bunch of stuff on the scope. Now that I've got this great mixed domain, or mixed signal oscope, I can get the power waveform on there, I can get the Ethernet. I've already got the Ethernet broken out on the local side of the transformer here, so I think I can get back to the state I was at before, where I was using the logic analyzer to view the Ethernet as if it was just 3.3 volt TTL. That was working because it was DC coupled, and I was seeing both sides as just these 3.3 volt push-pull driver outputs. And I think actually I can set that up with the logic analyzer again if I just put the transmit probes for this side on the other side of the transformer. So that should be, I think, pretty straightforward. And then I can start to verify some of my assumptions about timing and start to see if I can notice this this kind of real-time clock-based polling loop that I expect exists. And I expect I would see that, I would see some evidence of that in the timing of replies over HTTP and of GPIOs that are output from this program running on the PLC. I would also expect to see evidence of that in the power waveform. And most of all, I would really hope to find evidence of that loop timing itself against the external real-time clock, since that's kind of still my best bet for why I'm seeing the behavior that I'm currently seeing with the web server failing to work as soon as I underclock this below a certain point. So those are all questions that I hope to answer quite soon with this setup. So that might be on the agenda for tomorrow. A lot of SMA connectors going on here. I might end up doing a number of things with the FPGA setup here. Right now, I'm still pretty much rocking the thing with the chip whisperer, doing a little bit of the test orchestration and generating the glitch pulses, and then using this lattice iStick over here to do whatever else I want, which right now just means doing some clock generation, but this is actually probably a great place to put the emulation for the real-time clock if I end up needing to do that. This FPGA can keep whatever fake time base I want, and then I can write an emulation of the I2C interface that real-time clock chip usually presents. To go is not sitting in frame. Silly cat. All right, how do we go here? This is a little bit sturdy. Okay. That might be enough to handle, actually, for these next few experiments. Yay. Let's put some spacers on. Well, the hot glue gun. Well, let's keep the hot glue gun warm and put some spacers on this. So that kind of fits. Spacers. Oh man, it is so tempting to actually 3D print a little support block for this. Because I have these little spacers which I've been gluing onto the boards, but this one is actually really tall, and I need a cutout for the SMA. Let's just do that. I mean, I don't really care how long it takes to print because I can let it print overnight, and I don't think it's going to be a long one anyway. So let's do that. Oh. My usual CAD machine is the one that's installing updates right now. So let's use the slower machine that I usually do demos with. Those updates are still at 9%. I don't know if it's going to finish. I don't know. Let's see, where did we want to go? Yeah, because this would be really easy just to make exactly the piece I need to support this. So let's just do that. Oh no. No. For some reason, the autocomplete for Fusion 360 goes to the uninstaller. The actual app doesn't show up in the autocomplete. Let me go aim the camera better. Okay, so let's make a thing. Let's dimension this here. So I think I want to make this shape relatively simple. Let's make it wide enough for this whole thing, because why not? 40, call it 50. Just going to make a little square cutout for the SMA connector. 15 by 15. And it's another 15 from the I'm gonna go from the midpoint there up. From here. Okay. Thickness. Let's make that about 12 millimeters. Oops, that's not what I wanted. Okay, I think that's pretty much all I need, just this shape. Glue it to the wood on the bottom, glue it to the board on the top, no fasteners. Oh. Why can't I mouse? My space mouse stopped working. I think I might have locked the view somehow because I can't rotate with this mouse either. Okay, I appear to have broken the Fusion UI for myself in another way that I don't understand. That's fine, I'm done anyway. I just need to, it feels like I'm in some kind of face edit mode. Well, I'm just going to say this is an STL and move on. I clearly have some holes in my knowledge of this program still. No. No. Yes. Okay, 48-minute print. That's great. Can we just send it directly to the printer? I don't think Kira is actually going to send this file to Octoprint. That's fine. It sometimes works, it usually doesn't. Let's see if it's there. This was glitch bracket. No. Now Tuca wants to play Bolt. Maybe this is a good way to finish up the current operations. I keep saying that as if I'm going to end the stream soon, but then I keep finding something else I have energy to do. There you go. Oh, I feel like I should put red filament in there because there's so much red on this test setup. There's still blue in there right now. I don't think it matters. Red filament. And the cat still wants to play. Oh, we don't even know how to cat anymore. All right, I think this is a good stopping point. Print is underway. Yeah, so I guess the next things to do to this are to just do the soldering mods on this board. So attaching the cable for the glitch board, breaking out the memory, and then just see how much we can learn from all of that. I'm hoping we can see some interesting traffic to the memory chip, or at least get some interesting timing information from that. There's some other things that might be useful to look at. It's tempting to break out the SPI that goes to the display so that I can see when the microcontroller is busy updating that. But, you know, I suspect what's going to happen is there will be a little bit going on in the interrupt handlers but that's mostly going to be like third-party driver code, and I suspect most of what's actually going on as far as the PLC kind of main application here, I suspect most of that's just going to be in a loop that runs kind of round-robin style. So getting all of this on the same scope and putting it through some tests, I really hope to start to see some seeing some timing charts that let me see whether that's true or not. Get some more information about what's going on. Hey Tuco, you found a bolt. You brought me a bolt. Amazing. Mikey in chat suggests switching the filament color every half hour or so. Well, there would only be a couple of switches because this won't be a long print, but I've seen some prints where people went really crazy with the manual switches. Like the multicolor designs where you have to switch every couple of layers, but then the result is totally worth it or something. I think I did a switch when I was printing the little VFD that I have up on the pole there next to the scope. So you can kind of see that that's in a blue case right now. I printed that in blue and then painted part of it black. But actually I started the printer with clear filament in there because I thought that it might be interesting to see the circuit board in there. But then I just decided I really wanted a clean exterior look, and so I changed it on the first layer. I think the only thing that actually ended up being clear was the brim. Hey Tuco, where's the bulb? Oh yeah. Kyle asks whether IPA is the preferred pairing for voltage glitching. Probably. I think it works out pretty well. I also just really like hops. You can make it hoppier, and I'm pretty much always a fan. Oh man. I was excited to do some of that micro soldering, but I think that might be best saved for tomorrow morning. Spent so much time chasing that urge to just get one more thing done, and I would stay up so late, especially in my teens. So many all-nighters just because I had to finish the thing I was doing. But I feel a bit more relaxed about stuff now. Like, I think some of what drove the all-nighter was, oh man, I've got to get everything done now, otherwise I've got to get up and go to school in the morning. But in this case, well, I'm just going to work on this some more tomorrow. So it's, the context switches being more under my control is still sort of weird, but I like it. It's just not quite sure what to do with the freedom at the moment, except try to enjoy it and mostly fail. I really don't know how to be an adult. But I don't know. I think part of what I enjoyed learning in my kind of late 20s / the beginning of my 30s is how much most adults don't really know what they're doing, and a lot of being an adult is kind of an illusion. A lot of people seem like they know what they're doing because they're following patterns that are well established, but they might not necessarily understand why these things are established. They might just be doing them because they're familiar. I think Tuco's getting what he wants, just a little bit. Yeah, I like that. Mikey says, we don't grow up, we just learn to conform more. Yeah. Yeah, some of us spend a lot of our lives trying not to conform. And then figuring out all of the things that ends up entailing. I mean, conformance and nonconformance are each complicated in their own way. Conformance has so many different flavors and subdenominations. And then nonconformance is always at odds with itself and always questioning, or at least it should be. Tuco, are you satisfied? Kind of? Wow, did I satisfy Tuco? Or is that just a bad throw? Can't tell, maybe it's a bad throw. Yeah, Tim says school isn't made so much for teaching as conforming. Well, that was my experience of school for sure. I occasionally hear from people who had a good experience with school, but it largely seems to be based on finding individual relationships that helped them grow. And for me, that never really seemed like an option. And then school always turned out to be kind of adversarial. Like the teachers didn't really know what they were doing, and they were just trying to have control over the class. And it always seemed like I was just trying to find my own way of learning. Even if the things that they were teaching might have actually been things that I would have had fun with, just because it was their thing, I had to go find my own thing and do it. So it was definitely adversarial. One of my, I think one of my favorite memories at this point of college is I took this digital logic class, and that was when I really was not spending that much time just doing the classwork, and I was more into like doing my own kind of research projects because I thought the classwork was so repetitive and boring. And so in this digital logic class, there was just so much repetitive stuff. Like there was some fun stuff that was, I don't know, like I enjoyed the stuff where we had to solve something from scratch, or like design and build something, out of gates. That was fun. I didn't like so much when they made us solve like the same problems over and over again by rote. That just seemed like, okay, I get it, you're just wasting my time. And so I ended up not doing a lot of the homework, and I actually got a pretty bad grade in the class. I think I probably got like a D or something, or maybe something in that neighborhood. And then the final project comes along, and it's just like this open-ended thing that you can design on an FPGA. And so I remember bringing in my own FPGA, and it was a Xilinx XC4010, which is pretty small, but a little bit bigger than what they were usually using in the class. And it had some SRAM, and it made a Space Invaders game. It was like entirely in schematics because there was some rule in the class against using HDLs at the time. So it was all digital schematics, all these counters, and digital logic for sprites, and addressing all the different Space Invaders and the player character, and it had buzzer music and stuff. And I remember showing that, and the professor and the TAs were just like blown away by that was just running in hardware without a soft core or anything. But then, I think I still ended up getting a bad grade in the class because I didn't do the homework. That was kind of my approach to school. It was kind of weird. The adversarial relationship was not so good. I would have rather had something else, but it led me to do a lot of my own stuff at the time. Oh, nice. There's a good discussion in chat about schools also. Kyle's mentioning, Kyle says, my first semester, my GPA was literally 0.666. Yeah. And then he wound up teaching for the same university afterwards somehow. Yeah, I have friends who, that story reminds me of, I don't know, I have a friend who was in grad school for the longest time, and I thought she would always be in grad school. And she eventually got an industry job where she is now, but I don't know, like she was this weird combination of, not really being compatible with school and, always kind of working against the grain of what the classes and the grading systems would have her do, but at the same time being, one of the smartest people in the department and, teaching classes and, having an interesting, somewhat adversarial relationship with the staff. That seemed interesting. It wasn't for me, but I could see how she got there. Epoxy on a stick. Tuco, you brought another bolt. Are you not completely done with this? I was like starting to pick this up and play with it, but it isn't actually totally cured, so now my hands are slightly sticky. Sorry. Tuco, how about I throw you the bolt with the other hand? Alright. As fun as it might be to throw the bolt and watch this entire 3D print happen, I don't think that's quite necessary. I think this is probably a good time to wrap up the stream, and we will pick this up tomorrow. We should be getting onto some fun parts. I'm really anxious to see how these timing diagrams look after we've actually got the probes on. I was getting really bummed out by how inaccessible all the signals are, but this should be much better now. So that should be pretty good. Alright, I'm gonna wash the epoxy off my fingers and maybe throw a few more bolts before bed. Happy hacking, everyone. See you next time.